good afternoon, everyone. So my name is Xiangang Wan, come from Nanjing University. So today, first of all, I want to thank the organizer give me this opportunity to report what we recently are doing. So first, I want to thanks my collaborator. So Feng Tang is my PhD student. He's doing a lot of hard work. And then Professor Ashwin, he's in Harvard University. And then Dr. Paul is his PhD student. So we finished several papers. So today I will mainly focus the first paper is actually describe our method. So today I will talk about the symmetry indicator method, especially I will tell you how we can quickly check all of the atomic limit. Yeah, we can completely search all kinds of atomic limit, and then to compare if this guy is not, they cannot go back to atomic limit. They will definitely have some topological something. That's the idea. So and then I will also talk about some topological materials we describe. We find. Okay, so I don't know why they have like this one. Okay, but anyway, I can do in this one. So as we all know, topological basically is a mathematical concept. Okay, they describe. Okay, if we can continue change on any kind of shape. If they have something don't change. Okay, it means topological equal, right? And then for physics, we usually use in the symmetry. Okay, it's all the parameter. Basically, it's Landau phase transition theorem. So and then I think it's I think it's a start from 40 years ago, more than 40 years ago, and then people find the quantum Hall effect. And then to study the quantum effect, people realize if they have something, it's global. Like topological, it means it's global. And in physics, you can do in that in the system automatically. If the band gap don't closing, you can do it automatically, right? And then there was something don't change. So and start from that, the topological concept go into physics. Okay. So for mathematical is continue. You can continue change that one. You don't start that one, right? And then for physics, okay, there always a gap. Okay, they always have a direct gap, and then you can do in that arithmetic transformation, arithmetic doing something, right? So that's the idea. So and then if you can do arithmetic doing something, they have something don't change. What is don't change? The thing don't change. People call it topological invariance. Yeah. So if the system have a time reverse, symmetry, people are saying that J2 topological invariance. They have something don't change. Okay. If you broken the time reverse symmetry, the chain number don't change, right? So and then. That's just the idea, and then how to check if the material is 3D topological initial or not. Okay, you can calculate surface state. You can check surface state. You can automatically connect two band. Okay, you can automatically connect two band and then check it is topological or not topological. You can check does they have band inversion. What means the band inversion is SPD. Okay, or here is in this high symmetry point. In Boolean zone, S band is higher than P band. In the another Boolean zone, high symmetry point, maybe P is higher than S, so this band inversion. But the most direct way to check the 3D topological initial is directly calculate J2, right? So if people are talking about 3D topological initial, it means they will have a time reverse symmetry, and then you calculate J2, right? You need to calculate J2. But calculate J2 is not easy job. If the system has inversion symmetry, and then full and then they realize we can use inequality of occupied band to calculate J2. But if unfortunately the system without inverse symmetry, and then you need already calculate J2, basically it's J2 basically is related with the phase of the wave function, and then you need to do in the that kind of calculation definitely is not easy, right? And then it's not an easy job. So and then to find the topological insulator, it's not easy if the system without inverse symmetry. And then, but here I want to emphasize the topological is protected by time reverse symmetry. But you can use in the inverse symmetry to check. Okay, that's different. Okay, and then in addition to inversion symmetry, in time reversal symmetry, they also system have also like particle Hall symmetry, and then also Kylo symmetry, right? Okay, so people check which instead of time reversal symmetry, another symmetry what the other symmetry can affect, okay. And now also topological, definitely topological show the link with the dimension, right? Okay, dimension is 1, 2, 3. So and then people they make this table, a great table to tell us, okay, which possibility. That's just a possibility, yeah. It's a possibility. And then this time reversal symmetry, Kylo symmetry, and then particle Hall symmetry is not all, right? And then for the crystal structure, crystal symmetry also can protect something. So and then this first one realizes Liang Fu realized, okay, crystal symmetry can also bring some new stuff in that topological community. And then they also have two very great paper. So it is a topological crystal insulator. And then nowadays they have a lot of topological insulated stuff, yeah. Topological insulated phase, like a Miller-Chen insulator, hourglass fermion, water paper fermion, and then high order topological insulator, especially high order topological insulator is quite interesting. Here, as we all know, topological is if the system is d-dimensional, and then you check d minus 1 is either first surface state or H state. But for what is high order topological insulator, it means if the bulk is d-dimensional, and then you look d minus 2 or d minus 3. So actually, I think it's 3 years ago they have 4 group realized they have they have high order topological insulator. And then nowadays people are all talking about the insulator case. Why people want to talk about the insulator case? It's automatically you can do something. So topological insulator by definition it means topological should be insulated, right? And it's possible for metal. Almost 10 years ago, I am doing this particle EDJs. It is a complicated magnetic structure materials, and then I figure out that the magnetic order for these materials, and then what we are doing is we doing the LDA plus U, and then of course we need to change the U, right? We change the U a little bit. If U equal to 0, this guy is metal. If U equal to 1.5, you can saw it's insulated, right? And then I increase a little bit, U equal a little bit more, U equal to 2, it is still insulated, but it's very, very strange. If we increase U, the band gap becomes small. It is impossible, yeah. So as we all know, LDA plus U, we are using Hartree Fock. We are using the mean field approximation. This definitely told us if you increase U, the band gap will definitely increase, So there's something is wrong, yeah. So we are thinking what happens here. So and then eventually I think, why we don't calculate the parity? So I calculate the parity, I think, parity change, Parity change, it means, they may have some topological stuff. And then we are going to make a K dot P. And then we realize it's not a topological insulator, it's topological metal. It's topological metal. And then this topological metal, you cannot kill them, You cannot kill them, yeah. It is very, very robust, It is very robust. And then moreover, they have fermionic, as had been already discussed by Bing Hai. So this is quite interesting. So start from here. So topological semi-metal or topological metal, go to that community. But unfortunately, the compound we are talking about is still not conformed by experimentally. So the compound had been I have no line. Here. No, it's no. So this guy is I think it's 2015. Actually, it's IOP group in Beijing, also Princeton group. They independently find the compound TAAS, and then this their theoretical suggestion immediately be confirmed by experimenter. There are 2 experimenters. One is came from IOP in Beijing, another is again in Princeton University. So why people are interested in the topological semi-metal stuff? There are several reasons. So they have current tunneling. They also have a fermionic, and then also have a Kylo anomaly. So they will affect the transport transport property. So as we know, we are interested in the transport property, right? It's quite useful. So and then I take almost 10 minutes to tell you topological now is a big family. So we have a topological insulator phase. We also have a topological semi-metal phase or topological metal phase. So they have two. They have so much concept. Okay, so much this or that. Okay, then a big problem is how to find the materials. How to find the materials. So they have so much topological blah blah blah. It means okay, they may have so much topological invariance, right? And then you need to calculate that one. And then you calculate? How you calculate this one? You're using the wave function. You're doing the wave function integral in the Huo-Brilliant-Zhong. Usually it's slow. Basically, usually it's slow. Okay. And then also you need to calculate all kinds of right. If it's not J, it is J2. If it's not J2, you need to check it's a middle chain. It's not a middle chain. You need to check it's Western metal. If not Western metal, you check okay the X metal. So usually it's not that efficient, right? It's not that efficient. So to find any good topological materials is a big success. At before, yeah, at least at before, yeah. So and then people are thinking, could we go a little bit better? Could you do a better work? Okay. So basically, they have two ways. The number one actually is I think it starts from Fu and Ken. As I already told you, so if the materials have an inverse symmetry, we can use in the eigenstate of the inverse symmetry, the eigenstate of the inverse symmetry parity. We can use in the parity of occupied band to calculate the J2. Okay. Inversion is a lattice symmetry, right? And then lattice have a lot of symmetry. So people try to use in this symmetry to calculate the topological invariance. So along this, actually, there are a lot of people doing great work. Okay, including I think it's Chen Fang now in IOP, and then Borlaug at Princeton, and then Fu Liang is in MIT. So there are a lot of guys doing that, just using the lattice symmetry to calculate the topological invariance. People want to avoid the wave function integral. That's quite heavy. And then another direction actually is to check the mismatch between the Liouville space and the momentum space description of band structure. Basically, I just follow this direction. Okay, in this direction, they have two very great work. It's very good paper. So the first paper I think is done by Borlaug and his colleague. So Borlaug introduced great concept is topological quantum chemistry. They are saying, okay, due to time reason, I cannot explain a lot of detail. So actually, Borlaug introduced element band representation. This idea, he introduced, okay, connect figure or disconnect figure, and then they can use this one to check the compound it's topological or not topological according element EBR, element band representation. This is a great work, and then people can really use this method to check it's topological or not topological. But to me, it's quite complicated. First of all, to me, I'm not familiar with all kind of that figure. It's a figure like that kind of figure is not. We are not familiar with that kind of figure. And also, they have too much. They have 10,000 of EBR element band representation. So it's hard to use for me, at least for me. And then another great work is done by Ashwin and his career. And then this paper is quite a mathematical paper. They just check all kind of possibility. For example, space group 81 at J2, they have two possibility. And then space group 82 is also two possibility. And then space group 52, they have four. J4 means four possibility. That's it. Okay. And then what is J2? At that time it's still not clear. It's not clear. So this paper is clearly told us possibility. But actually, this you cannot directly using this paper to check the compound. And then again, this paper is great, and then you can use this paper to check the compound, to check that it's topological or not topological. But it's, at least for me, it's not easy to use, yeah, at least for me. And then this paper is told us the possibility, theoretically told us the possibility, but it's not You cannot directly use it. Yeah, you cannot directly use it. So we go based on that, based on those all kind of this work. We are doing a little bit more. So what we are doing is I'm thinking why we don't quickly check all kind of atomic limit. Okay, that's our idea. So and then I will tell you our idea. So number one is that's a band structure of the silicon. That's the band structure of silicon. And then the silicon, the space group is 227. That's the silicon band structure. And then usually people ask, Xiangang, which code you are using? WASP or Win2K or Siesta or So and then which LDA, GGA or but they all detail. Why? So as we all know, topological global property, right? So and then as I keep to tell you, if that direct band do not close, it means you can do arithmetic. You can arithmetically change, right? So you arithmetically change the band structure a little bit, Like here, this band, is up or down a little bit. Nothing happens, From topological point of view, doesn't change, So if you don't close in the direct band gap, nothing happens in topological point of view. And then, so we don't care the detail. So what is the detail? It's actually, and then this is a band structure, right? Band structure, this is drawn in the Boolean zone. In Boolean zone, we have, high symmetry point, high symmetry line, and general point, right? And then they have infinity general point. We cannot check all kind of general point, So the easiest way is, to check the high symmetry point. The high symmetry is quite limited. It's just few high symmetry point. And then we look about the high symmetry point. And then how we check the high symmetry point? We all know, is S band or P band or D band. This is not correct. This is not a correct language, right? So and then what we can do is only we can talking about the high symmetry point representation. High symmetry point, they have a little group, right? The little group will have a representation, using that representation to lamp the band, to lamp the band. So and then here is a number. So here I'm sorry, I just using my finger. So K1 tier K1 K2 tier Kn is how much high symmetry point we have. And then this one 1 2 is for this K1 how much representation they have. They 1 2 3 4 this is 4 representation. So we usually using this number to describe the occupied band, For the all kind of occupied band in high symmetry point, how much representation had been occupied, So we are using this number to lamp them. So why this number is useful? So if this number happens, if this number change, it means band definitely close, Band definitely close. If this number don't change, it means that doesn't happen, So it's something like that one, And then another interesting structure I will tell you is, if we add 2 band, For example here, now we have 1 2 3 4 4 band, 4 occupied band. If we draw another band here, we just do in the plus, We just do in the plus. It's very simple. For this new band, you can also get this one. And then for 5 band, now it's for 5 band, occupied 5 band, it's just simply doing the plus, It's just simply doing the plus. So that's one thing I want to tell you, how to efficiently lamp the band, How to efficiently lamp the band. We just check the high symmetry point, Of course, we will meet something, but okay. And then another idea I want to tell you is atomic limit. What is the atomic limit? If it's only one atom here, it's a complete empty. It's only one. This is atomic limit, right? And then if you put the atom close together, and then if you form a solid, then maybe it's atomic limit, maybe it's not atomic limit. And then let me assume, if you have one unit cell has only one atom per unit cell, and then this one atom have only one s orbital, and then they can form 2 band, right? They have 2 band, up down, spin up down. So they have 2 band. So they have all kind of possibility. But you can say this has without the band closing point. These two cases with band closing point, right? But it doesn't matter. If these two bands, if the Fermi level is the top line, if the Fermi level is top line, it means, okay, in other ways, if these two bands had been fully occupied, it doesn't matter. These three cases is exactly the same. It can automatically go back to atomic limit, right? It can automatically go to the atomic limit, yeah. But if the Fermi level is here, dash line, you cannot go back to the atomic limit. Why? It's okay. Two band is an atomic limit, right? If it's half, it cannot be. It cannot be. And then, but this language is not correct. Using the one unit cell have one atom is wrong. And then S orbital is also wrong. Why? The reason is very simple. So you cannot put atom in space group. You can only put atom in the weaker position, of a particular space group, right? That's number one. Number two, S orbital, P orbital, D orbital is not well defined. So what is well defined? It is a side symmetry. For example, this guy, the space group 2, and then space group 2i, they have side symmetry. That side symmetry's representation have a meaning. So we should using this language. So and then we doing this again. Okay, for space group 2, how much point we can put? It's lie. We can put the lie point. Okay, we can. First you put 1a. You put an atom in 1a, but how much orbital you can put? Now this is not real orbital, it's pseudo orbital. It's not S orbital, it's pseudo orbital. There are two representation. It means they can put two selection put in. And then if we put the first representation, you form a band. It's definitely as I already said, it's atomic limit. And then you can put another. It's also atomic limit. So sum together, how much atomic limit you got is 17. So and then that's the idea. It's a very simple idea. And then any compound should do like this one. So for example, particular iridase, I studied several years ago. And then if you go into a book, okay, they will tell you, oh, this atom sit on this weaker position. This atom sit on this position, weaker position. This guy is in this weaker position, right? And then you can calculate this one, and then eventually you got this one. And this M is I already told you several slides ago. Yeah, several slides ago. So it's just in the plus. Okay. So using this way, so if the compound is space group 2, any compound, I don't mind. Yeah, any compound. So and then the atom should sit down in this weaker position, right? In all kind of this position. If it's not sit down in this position, it is not a space group 2. It's not space group 2, right? So and then using this way, we can completely check any kind of atomic limit. Okay, let me tell you how I can do in this one. So that's step 1 is how much high symmetry point we have. For space group 2, we have 8 high symmetry point. And then from a book, okay, from a symmetry book is a very big book, okay. They will show you the position in the Boolean zone, high symmetry point in the Boolean zone. And then how much weaker position they have is 8. It's lie here. It's 1a, 1b, 1c, 1d, tier 2i. And then 1a, the side symmetry is ci. The 1b side symmetry is ci. And then tier 2i, the side symmetry is c1. So, and then in space group 2, we put the atom in 1a, and then select the orbital. Ci have 2 representation. So we select the first representation. Okay, we got it. We found that we doing the block sum. Doing the block sum from the band structure. We can calculate this state. Right? This means atomic limit, as I told you. This is completely occupied band. Definitely is atomic limit. So we can do in this kind of logic. How much we got is 17. This we don't need a computer. We just use a laptop can do in that job. We don't need a cluster. This is all done by laptop. Yeah, all done by laptop. Okay, then we calculate the atomic limit. And then we got this one. We got the whole table of the atomic limit. And then it means any atomic limit show the linear combination of these 17. I don't want to say vector, okay? It's still not vector, okay? It's not vector. And then you may ask Xiangang, does this guy is linear independent? It's not, yeah, it's not. Actually, Ashwin has a great paper. They had a great paper. They extend and then introduce negative number, and then make this guy has a vector. If this guy had become a vector, and then we can check, okay, the base vector, right? We can check the base vector. And then we got a base vector for this guy. That's the base vector for space group 2. That's the base vector for space group 2. And then we calculate any compound. So here, for example, so we take from the database or from everywhere, from whatever you got the compound. And then if you got the compound, definitely you know the space group, right, for that compound. And then we can, they will totally have 230 space group. They have 230 space group. For any space group, we can calculate the atomic limit, base vector. And then we store in somewhere. To finish this step, just only half an hour in the laptop. And then here, for this step, is you are using the DFT calculation. You calculate the occupied band. And then you calculate the representation in high symmetry point. And then got this one, and then using this guy to expand this one. If this Q is integer, they have a possibility to directly go back to atomic limit. It's not definitely it is, but they have opportunity. If this guy is not integer, they have no way to go back to atomic limit. So that's the idea. So it's very, very efficient and very simple. It's very simple and also very efficient. So and then I think I still have a few minutes. So I will show you the compound we find. Okay. So then the first example we show in our paper is MOTE2. Why we show this compound? This compound is very hot, as I had already been told. This compound is very hot. Okay, this guy is in room temperature. Molar layer is quantum hot, and then gamma phase is type 2 Western metal, and then they have a lot of discussion. And then how we calculate this one? For this compound, the space group is 11. Space group 11, and then how much valence electron is 56, and then that's the detail of this compound. So for how much high symmetry point they have is 8 symmetry point, high symmetry gamma point, B point, Y point, okay, TRE point, and then this second line we show is what in gamma point they have 1, 2, 3, 4. The little group in gamma point have 4 representation. And then the second number 1, 1, 1, 1 is the 4 representations, all one-dimensional representation. And then B point is also B point. The little group in B point they have 4 representation, 4 one-dimensional representation. And then for J point have only 1 representation. This representation is two-dimensional. But this guy, if you have time reverse symmetry, this guy can double. So this basically, if you have a time reverse symmetry, the degeneracy is 4. Yeah, the degeneracy is 4. And then that's the first line, the second line, and then third line is you calculate the band structure calculation. I'm using Win2K. PPE calculation, and then double check by MBJ. So and then that's for gamma point, we have 16 band occupy the first representation, 16 band occupy the third representation, 12 band occupy the third representation, 12 band occupy the fourth representation. So something like that one. Okay, so we got a number like this one, and then we using this guy. That's the atomic limit base vector. That's the atomic base limit base vector. We're doing the expansion. We quickly got, this guy is not integer. It means topological something. But as I told you, we do actually at that point we don't know which kind of topological. We don't know which kind of topological. And then they have 2 great paper. they have two great papers told us, okay, which kind of group. You need to do in additional calculation. And then what we need to do? We need to do the Miller-Chan calculation. And then we calculate the Miller-Chan number, find Miller-Chan number equal to 0. It means they have a Hange state. So and then that's the numerical result. Actually, as you saw, they have a Fermi pocket. Okay, they have Fermi pocket. This guy is not a very good insulator. They have Fermi pocket, but they have direct band gap everywhere. But okay, this MOT2 is so hot compound. So I'm thinking we should take this guy as the first example. If we are wrong, definitely people are pointing out we are wrong. If we are correct, okay, I think okay, maybe we will be conform. So we got a Hange state something like this one, and I think luckily we put in the archive, and then luckily I think few days later, actually Binhai they also doing a similar work. Okay, they're also doing a similar. I think it's independently doing a similar work conform. This MOT2 it's interesting stuff. They have Hange state something. So it's that's something. That's the first compound we show. It's not a very good compound. It's not a very good topological. And as you saw, the Hange state is not that good. Okay. And now, but okay, of course we have a good example. But we take this guy as the third example. Seems this BI is not that famous. Okay. It's not that famous. And then okay, we find they also have a Hange state. They also have a Hange state, and they also have a Dirac point somewhere. And then our result is also confirmed by Layton's study, by others' study. So, and then we also using this guy to check. As I told you, if the system had a inverse symmetry, you're using the full can, using the parity to calculate the topological J2, right? But if the system without inverse symmetry, it's really hard. Yeah, you need to calculate J2. You need to calculate J2. And then here, using our method, you can avoid that one. Okay, we find okay this guy is a topological insulator, but it's without inverse symmetry. We also calculate. Okay, we find our glass Hange state weak topological insulator, a strong topological insulator, and also Dirac semi-metal, and then third fold, okay, is high degeneration point, a lodolite semi-metal. So seems our method it look like it's quite efficient. So we design why we don't check all kind of database. Okay, then we take ICSD database. As we know, in ICSD, they list about 80,000 compound, but most of the compound has a disorder or impurity. That it's not easy to calculate that one. So and then we do not consider a compound. And then we also know the regular DFT calculation is not good for 3D, 4F, 5F. So we don't calculate this one. For several 4D, 5D element, the Coulomb interaction is also okay. DFT is also not that good. Okay, so we do not calculate this one. So totally, how much compound we check? Okay, it's about 90,000 compound. So for this compound, we can definitely know this is without it cannot be magnetic, right? It's definitely with time reverse symmetry, and then we calculated of course we consider spin-orbit coupling. We using the Win2K GGA double check by MBJ. So you may say, okay, Xiangang is very heavy calculation. No, we finished all kind of calculation in about one month. Using my cluster. I'm not using our university computer. Yeah, we don't need. Yeah, it's a small computer, as you can saw. It's a small computer. So and then we find a lot of topological materials, and then we build a database to list all the compound we find. Okay, we list all of them. And if you're interested, you can check this. This website, and then okay, I skip all of them. And then I should mention we actually at the meantime, okay, IOP in Beijing And then also Princeton University doing a similar work. Okay, they also build their own database. Okay, their method is a little bit different. Though. We are using the symmetry indicator based on to check the atomic limit. And then this paper actually they just using high symmetry point representation to calculate the topological invariance. And then this guy is using the topological quantum chemistry. Yeah. It's a biological school. So we are doing a quite similar job, but the method is a little bit different. Okay, and then I also should mention actually we only look the high symmetry point. So we will meet something. For example, this guy TAAS we cannot check it. Okay, it's in general point. Also, currently the magnetic is very hard. The magnetic why it's hard is magnetic structure. It's not easy to determine. It's not easy to determine. So that's the conclusion. We propose efficient method. So it's easy to use. Okay, it's quite easy. So we just look one number. It's integer or not integer. It's not integer. We take a look. Okay, if it's integer, we don't look. Yeah. So that's quite simple. And then we propose a lot of compound. So and then actually we finish. It's not only 4 paper. We also recently we also finished the two-dimensional materials. Okay, but unfortunately, two-dimensional materials without a big database. Yeah. So thank you for your attention.
Questions to the speaker? Yes.
You mentioned the 2D material.
Yeah.
The 2D one. There's some interesting topological phase. Something new.
They have something, yeah, but it's not. It's not. You know the point. The most problem is that they're not too much. They're not too much two-dimensional.
I see.
Yeah.
They're only like topological insulator.
Topological insulator. Yes. Yeah. Something. Yeah. SPO. Yeah. Not much. Yeah. Okay. Not much.
Any other question? Well, since you started comparing, let's say, your database with the one from Andrei Bernovik and from Beijing, so
yeah,
would you comment on the differences? So, I mean, of the final result of, let's say, the number
very
of
similar,
candidates?
very similar. The final result is very similar, yeah.
Is there any material that would come from your predictions and would be confirmed experimentally? Something that would not be possible before you did this, or?
Oh, I'm not follow much, you know. So I think they have several. They have several compound had been confirmed, but I'm not follow. Yeah.
Any other question? Well, if not, let's thank our speaker once again. So I'm closing this session. Next is the coffee break.